Okay, so thank you very much. Good morning, everyone. Let me start by thanking warmly the organizers, Tommaso, Shamik, and Romain, for a very nice invitation. It's my second time in Natal. My first visit was before the new institute, so I'm pretty impressed by the developments. So today I'd like to present to you our recent results on the quantum dynamics of relations and response in long-range spin models. The title has been slightly changed to be more specific. And let me start by acknowledging the people that made this possible. In fact, Irene Ferro, who's a postdoc at ICFO, Peron Aldesi, who's a postdoc in Grenoble, Rafael Menu, who's a PhD student at my supervision, and Lorenzo Cevolani, who used to do physics. Now he's a software engineer, but he does physics in the spare time, working on long-range interacting systems. Okay, so this workshop is about classical and quantum systems. So my talk is about systems. I suppose it would be beneficial to have a little introduction to the classical side of in particular. So why it's interesting to study the dynamics of long-range interacting quantum systems. The topic about quantum dynamics has to do with the dilution of information that happens in quantum systems. So in particular, you can start, you can initialize a network of quantum degrees in a state factorized. So that means you attach a specific microstate to every degree of freedom. Inevitably, the Hamiltonian evolution will bring you to a situation where the information on the state of individual degrees of freedom is diluted across the network. So that means that individual degrees of freedom acquire a finite entropy, which is entanglement entropy, or you can think of groups of degrees of freedom. Okay, so and this goes under the name of information through quantum dynamics, because it may remind you what happens when you eggs that have initially their identity and then you scramble them together. Okay. In the context of quantum dynamics and the scrambling of information, work in recent years. Three common questions that are asked, in fact, in general by the recent literature. The first one having to do start with a state that has no correlations to it. Also take to know the network of interacting degrees of freedom. How long does it take to correlate them if they are at a particular distance r? A second question, which may look related, but you may have different answers, is take your system divided into two subsystems. You can ask yourself, how long does it take for the two subsystems to become entangled if they were not so in the initial state of the evolution? And is there a characteristic time at which they become maximally entangled as admitted by the dynamics? And then a third question is actually state independent. It's a statement about Hamiltonians, and you can, and it concerns the maximal speed at which Hamiltonians can propagate signals spatially in quantum mechanical systems. So these questions appear to be fairly related, and in fact, in the case of short-range interacting systems, the answer to these questions is essentially one and the same, which is quite reassuring in some sense, or even you can consider it to be a little bit boring. On the other hand, in long-range interacting systems, instead, the answers to these questions can be very different, and that's going to be the main subject of my presentation. Let me specify the discussion to a specific class of models. So I'm going to discuss long-range quantum magnets, long-range XXZ models, or long-range transverse field Ising models that are workhorses for theoretical studies, as well as, in fact, models of experiments, or beautiful experiments on quantum simulators, especially on cold atom-based quantum simulators with drag atoms, magnetic atoms, trapped ions. And these models and these setups have received a tremendous amount of attention lately, so a large body of theoretical work that I'm just in complete manner. In fact, many of the main contributors to this work are sitting in this room, or will be sitting in this room later this week. And also there's been a very nice set of experiments realizing precisely this power law interacting quantum spin models, XXZ and Ising, okay, based on trapped ions, magnetic atoms, drag atoms, and maybe other platforms that I'm forgetting here. All right, so when it comes to the theoretical description of the dynamics of these systems, of course, that's generally a very hard problem. And we have tackled it using the simplest possible approximation that retains the quantum mechanical description of the system, or in other words, using the simplest quantum field theory that is solvable, that allows you to describe the dynamics, the quantum dynamics of the system, which is just taking a harmonic approximation. So the underlying assumption of our study is that in the regimes that we are interested in for these Hamiltonians, the ground state is faithfully reproduced by a mean field approximation. So its physics is at least qualitatively captured at the mean field level. And so for spin 1/2 spins, you can attribute within the mean field ansatz a particular state, a particular spin orientation to every site. And then the idea of the approximation, that's very well known, I mean, the approximation is that you define a local quantization axis aligned with this local mean field direction, and you map the spin deviations with respect to the full alignment along the local quantization axis in terms of bosonic quasi-particles. So we have this spin boson mapping. And if the number of quasi-particles is sufficiently sufficiently low, then you can authorize yourself to have a non-interacting description of these quasi-particles or a harmonic approximation to the bosonic Hamiltonian. And then analyze this Hamiltonian and get the eigenfrequencies of your system. And this all works to the extent that the quasi-particles form a dilute gas. Okay? Or in other words, that the misalignment of the spins with respect to the local quantization axis is small. All right, so when it comes to dynamics, you also have to specify the initial state. And the initial state that I'm going to discuss throughout this talk is very convenient. Theoretically, is the mean field ground state, which is not an eigenstate of the spin wave Hamiltonian. So this state has many advantages. Again, it's technically convenient, but it's also very much related to experiments because it's a state that is perfectly factorized. So it's the kind of fiducial state that states that experiments naturally initialize the systems into. And from the point of view of these bosonic quasi-particles, it's just the vacuum. And then if you turn on the Hamiltonian dynamics, what that dynamics does to you is to create pairs of quasi-particles that are entangled, that propagate in space, and thereby entangling and correlating the degrees of freedom in your system. And the spin wave description of the dynamics is faithful to the extent that the diluteness condition is preserved during time. So the population of quasi-particles that are generated by the Hamiltonian dynamics remains under control, and it's small. All right, so introducing quasi-particles in the picture has a very nice effect of being able to answer in one sweep to the first two questions that I posed in the case of short-range interacting systems. Because for short-range interacting systems, quasi-particles have a finite group velocity that defines somehow the maximal speed of propagation of signals in your system. And so like in relativity, there is the existence of a causal cone around every point in space within which correlations develop at a particular time. And that's defined by the propagation of the fastest quasi-particles in your system. So the aperture of this cone, it's actually given by the maximal group velocity of the quasi-particles. All right, so this picture also tells about the spreading of correlations, but also about the spreading of entanglement, because quasi-particles, as they move, they entangle the region that they've covered. And then you can get a sense of how entanglement grows in the system. If you consider a bipartition of your system into A and B, the entanglement of A with B will start to saturate when quasi-particles have traveled across the region across the linear dimension of subsystem A. That means in a time that's linear in linear dimensions of A. Okay, that's the general answer then to the question of spreading of correlations and entanglement in short-range interacting systems. Of course, I wouldn't be talking about all this if long-range interacting systems were not introducing new dimensions to this particular context. And so in long-range interacting systems, one can find easily that entanglement and correlations do not spread in the same way. And to exemplify this statement, let me consider a relatively simple system, which is but very effective in my view, which is the long-range XX model. So just a ferromagnet interactions among the X and Y spin components and power law interactions. So this system, depending on the exponent alpha of decay of the interactions, has three fundamentally different regimes, two in particular I will discuss today. So in general, it has a gapless spectrum, but the dispersion relation close to the zone has in fact a different form. It depends on the dynamical exponent, which is equal to 1 if alpha is larger than d plus 2, d being the number of dimensions. And so the convention sound like dispersion relation, but the dynamical exponent z actually becomes smaller than 1. It continuously interpolates between 1 and 0 when alpha goes between d and d plus 2. And so that means that the dispersion relation becomes sublinear and close to the center of the Brillouin zone, and the group velocity diverges as you go close to the center. Okay? Whereas, it vanishes always, as you go. You get a large spectrum of different group velocities from infinity to 0, actually the largest possible. All right, so when you look at the spreading of relations, then in the case of short-range interactions, or if you wish, of alpha larger than d plus 2, you get nice light cones. You have a well-defined maximum group velocity, and everything goes as advertised already. But if you look instead in this regime for alpha between d and d plus 2, in this case, alpha equal to 2 dimensions, it's smack in between. You have a z that's more than 1, it's 1/2 in this case, and you see consequences of having a smaller than 1 technical exponent in the correlation spreading. This is for the z spin component, because, well, you see that there is some nonlinearity in the spreading. In fact, you can read out the z exponent by looking at how these correlation ridges evolve, and they are curved, and they look like square root of the distance. And then you could immediately conclude that the linear light cone picture is right here at curved light cones. So that means that correlations travel distances that grow like t squared and not like t. But this is a hasty conclusion, in fact. So first of all, is there such a thing as a light cone in long-range interacting systems? The general answer is actually difficult to give, because in short-range interacting systems, you have an exponential suppression of side of this causal region. But that's no longer the case with long-range interactions. For long-range interactions, you always have a tail, because without any retardation, in fact, interactions immediately correlate degrees of freedom at arbitrary distances. Okay, so in that case, there's no obvious front of correlations. Now, how do you answer to the question then about the existence of a light cone or not? There are two possible points of view that you can use. One in the point of surfers, you can go to Ponte Negra, ask any surfer out there. He or she would reply to you that, okay, so waves can well have or law tail in the front, but what I surf is not the tail, ridge. Looking in this correlation spreading for the ridge, if I regard them as being something in analogy with water waves on the ocean. And that's a strategy that's been used by Cevolani and workers a couple of years ago. They studied, in fact, the spin wave result for the spreading of correlations in the XX model, for instance, looking at the strongest contribution to the integral that defines this correlation function, treating it via stationary phase approximation. And what they allows them to define, it's a correlation edge component that relates non-linearly, possibly, space and time. And in fact, they find, for instance, that for these slightly surprisingly, the front or the ridge of the correlation front advances, in fact, sublinearly in time, or in other words, so you have ballistic propagation of correlations. So you would conclude that, okay, then correlations do the opposite of what you expected. They are subballistic. But then it depends on what you look at. If you look at another function, for instance, the one for the Y spin components, which was not discussed in this paper, the situation looks quite different. In fact, there seems to be a superballistic advance of the correlation edge in this case. So the answer is actually already multiple. But then what we personally contributed to the discussion was in a way kind of a funny replying to the question. We changed the question in some sense, and we asked a different question, which is what is the characteristic time for relaxation of local quantities as the effect of the propagation of correlation? Look at a subsystem of your total system, and you integrate the correlation functions in the monitoring the evolution of the local fluctuations. Do that, for instance, for the z-spin component. In that case, you're monitoring the evolution of the fluctuations of the total magnetization of the z-axis. That these fluctuations, in fact, relax in time with a characteristic time. It doesn't grow with a linear system you would expect if you had ballistic propagation of signals, but in fact, it relaxes over time. There are sublinear functions of the linear dimensions of the subsystem. In other words, the functions that reveals exponent z. So in this case, it takes a time that's square root of the size of the subsystem. Okay, so that would suggest that there is something that goes indeed super ballistic in these dynamics. So there are signals somehow that cover distances in a time which is square of the distance, and so they're able to make things relax over these time scales. But so not the end of the story, because that depends very much on which local observable you look at. You can draw different conclusions. If instead of looking at the integral of the function, you look at the Fourier transform, or in other words, the fluctuations of a Fourier component local magnetization, then the answer is very different, because what you're sensitive to in that case are modes that don't live at the center of the zone, which are actually, I didn't say, responsible for this super ballistic propagation. Sensitive instead to the modes at finite k, at the same k at which you calculate the Fourier transform. and these modes, they travel the widely different group velocities that go from infinity to 0. And so you have a multi-speed relaxation phenomenon depending on the observable that you focus on. So the picture that one can cultivate then is the existence of many light cones of different aperture depending on the quantity that you focus on. And what about the entropy then? So in all this diversity, the entropy introduces yet another element of diversity, because the entanglement entropy of a subsystem with the rest, in fact, takes contribution from all the modes. So in the presence of many modes, it has to patiently wait until even the slowest modes have traveled through the region of interest before saturating. And indeed, that's what's observed here. So the entanglement entropy relaxes over a time scale that goes linearly with subsystem size, in spite of the existence of quantities that instead relax over time scales that are sublinear functions of the linear dimensions of subsystems. And in fact, the entanglement entropy can also be obtained semi-empirically with the fact that it's a precise integral over the different modes that contribute. They give contribution that saturate time scales that are inverse of the group velocities of the corresponding modes. Okay, so the first part of my story. Are there any questions? The ansatz, it's some over modes. They are bosonic modes of their bosonic entropy, but there is a phenomenological function here, which is something like, so it's a function that grows linearly in time up until a time which corresponds to the time it takes for the mode to cover the subsystem, and then it saturates. If you sum these contributions, you get the dash curve here, and this compares to the exact of spin wave theory pretty well. Yes, that's true. And we haven't actually considered that case particular, because it becomes tricky because everything is a finite side effect at the point. But yes, you get a perfectly fat band, and then, except at k equals 0. Yeah. Not really. So we are, I think that as far as the low energy physics of the system is concerned, this is fairly generic. So we are taking a state which has the mean field state that sits comfortably in the low energy spectrum, and that allows the dynamics to produce not too many quasi-particles in such a way as to remain within the realm of the spin wave theory. Yeah, so changing the initial state, it can be done. I think the results wouldn't change so much, but it should be done indeed. Okay, very good. Okay, let's discuss to that. Yes. The time scales. Well, we'll look mostly at the scaling of time scales with. There's no energy in explicit, in terms of length or energy that we put into the theory that alters its low energy structure. Okay, so I think that does manifest. Yes. Excuse me. That's in the making. So we don't have an answer to this question, but we are gearing up to include nonlinearities. So I would say that there's a regime in which, at least a transient regime, where the quasi-particles are sufficiently diluted. You the vacuum, okay? So the vacuum is perfect. It perfectly fulfills the equation. So but there is no threshold beyond which you stop trusting your spin wave theory. That's the problem. So including nonlinearities would be a way to test how robust the picture is, though over which the description is robust. Yeah, so controlled, it's something that's controlled because it sits at a time scale, which is the inverse of the. So you can have when beyond the time interval over which you make statements, then your statements should be trustworthy. Yes. In D+2 primarily, yes. It's we call it medium range. Specifically. This and this that I just gave before, because the dispersion relation in that case becomes a bit anomalous, so it only manifests finite size effects. Yes, so I don't have an answer. Also, well, the z exponent becomes 0, and so you don't have these reference points to read out these space-time maps that you have for alpha larger than d. Right, so we continue then. Coming to the second, or no, the last part of my presentation. So I asked a third question. Remember, which was about the propagation of signals regardless of the initial state. And in fact, so this question is typically answered a setting that's called the study of spreading. The idea being that if you take a system of spins, for instance, and two sides, generally their spin operators at different sides would commute. But if you now time evolve one of the two spin operators in the Heisenberg picture, then you get operator not necessarily anymore, because the time evolution will actually give to the initially local spin operator components that are delocalized throughout the system, and that's called operator spreading. And it may look as if it was, a theoretical property of Hamiltonian of the operator algebra, but in fact it has tremendous physical consequences because in relationship with linear response theory. So if you prepare your Hamiltonian in an eigenstate of itself, and then you apply a local perturbation that's very short in time, like a field coupling to the jth state, then an evolution of the average of the operator at the night site. Well, this evolution is in fact governed by the dynamical susceptibility, which is nothing but the value of this operator, at different times. And if you want to have a optical analogy, somehow dictates, it gives you what you can call the space-time points function of local perturbation. So it tells you how localized perturbation spreads in time, localized both in space and time. Okay, and then if you want to make statements that are state independent, you can just maximize this quantity over all possible initial states. What you get is the norm of the commutator, which is an object then that governs fundamentally the space-time structure of the in the system. And this object has been the subject of a lot of research, starting from the by Lee, who actually found for the space-time structure, in the case of short-range interactions, a light cone picture. So this object here, the commutator norm, exponentially outside of a linear cone. All right, so that's perfectly coherent with what we've seen concerning correlation. Now, in long-range interacting systems, the situation becomes intricate. There has been tremendous activity to establish similar bounds to the commutator norm in long-range interacting systems, and these attempts, in fact, are still in the making, because especially in the regime, which is the most interesting one. I should say that some of the contributors to this topic are audience or will be later this week, hopefully. So you should refer to them if you want to know more about this stuff. I'm a particular expert about how you obtain these objects. But the most pressing aspect of the various alpha regimes that have been studied is the regime between D and 2D, which contains the regime that I alluded at, D and D plus 2 overlaps with it substantially. In this regime, the only bound that's known, again, it's not, predicts that the operator norm, in fact, grows exponentially in time. So that would suggest that there is an exponential propagation of signals, which is a bit statement in general. Also, in particular, in comparison with numerics. So all the numerics that has been done for the most part on correlation, equal time correlation functions, doesn't show this exponential propagation, as I've shown you before. And in particular, well, you have to be careful when comparing results on equal time correlations and on bounds on operator norms, because they don't relate necessarily unless you have short-range correlations. And this is definitely not the case for long-range interactions. So the comparison between the existing numerics and the theoretical predictions is not so obvious, and actually wasn't so obvious until very recently. This nice work by Barlev and Luiz, who attacked the problem straight on of the operator norm in spreading, and they did a brute force impressive exact diagonalization study of one-dimensional chains up to 30 sites. And their observation is that, in fact, the structure of these commutator norms is very simple. There is a part that obeys the same causal light cone of short-range interacting systems, so which spreads linearly in time, grows linearly in time, and then a part that leaks out of the linear light cone that decays like 1 over r or alpha linearly in time. Okay, and this is for all values of alpha that they could explore. You could answer that these are results that are limited in size and in time, so when you consider long-range interacting systems where finite size effects are dramatic. So it would be interesting to have an alternative approach to this, maybe an approximate theory that is not limited in size and time. And guess what the theory is? Well, it's spin-wave theories. And there you may react, somehow in a surprise way, because spin-wave theory, it's a low-energy description of the dynamics of your system, And now I'm trying to make statements that are based only on the Hamiltonian. They're not specific to the initial state that I start from. But working assumption behind using spin wave theory in a particular study is actually something that I think is very physically motivated to me. That's the observation that low excitations are the fastest ones. So if you capture them correctly, which spin wave theory should guarantee you to do, in some regimes at least, then you gain the correct description of the long distance and long time behavior of your quantities. Now, if you bear with me with this assumption, this is quite dramatic because calculating the operator norms, the commutator norms with spin wave theory, it's embarrassingly simple. You get commutators of bosonic operators, and they are C numbers. Okay? So you can get very simple expressions for these quantities. And actually, the bonus is also that comparison with the numerics that I alluded at, so far stands the proof. Indeed, if you look, for instance, at the one-dimensional Ising model with long-range interactions, these are data at fixed time for different values of alpha for the commutator norm of the Z spin components. You observe precisely the structure that's been observed by Lev and Lewitz, namely there is a short-range part which is common to any value of alpha that spreads linearly, and then there's a part of the commutator norm that leaks out of this linear light cone with precisely the 1 over alpha decay. In this case, regardless of alpha. So I'm also looking at alpha smaller than, and this picture stands. And using again the analogy with waves, you can view the large alpha behavior, like the situation in which the signals have a tail, but the mass of the signal is actually taken by the ridge. And for the small alpha, instead, you have waves that have a long tail in front, and they're very small, and maybe you cannot surf them. Okay? All right. And also, outside of the light cone, where you have this leaking, algebraic leaking of the operator norm, you observe a linear growth of the algebraically decaying part, as observed also numerically with exact diagonalization. Okay, so that means that we seem to be to confirm, or rather to corroborate, that spin wave theory gives a correct description, in comparison with exact numerics. And so that's the sketch of the whole picture, short-range part, and this this algebraic leaking with linear growth in time. And in particular, the separation between short-range and an algebraic tail, short-range part and algebraic tail, is pretty explicit in spin wave theory. You can prove it essentially semi-analytically by making a formal separation of the couplings between the short-range and the long-range part, and treat the long-range part perturbatively. But now, spin wave theory, if it works in 1D, it should be working in high dimensions as well. To 2 dimensions, where that diagonalization effect would be a lot more limited and probably almost useless. And in this case, well, we observe something very similar, looking at the 2-dimensional XX model with power law interactions, the one that I discussed already before. If you look at the operator norm spreading, of the commutator norm spreading for the Y spin components, it has, again, a linear light cone and a leaking outside of it. But looking at other the commutator norm for the V spin components, the structure is quite different. There you observe, in fact, an advance of the front, which is highly sub-ballistic, highly sublinear. So in this case, it appears as if distances advance as the cubic root of time. Okay, and also what I'd like to conclude the discussion is the commutator norms on the one side that I just discussed, and the correlations that I showed you before. If you have good enough memory, you will see that there are stark differences between the two objects. As a matter of fact, you can see generally that commutator norms develop in space-time much more slowly than correlation. So that means that linear response signals would travel slower than correlations. That's quite a strong discrepancy that's stabilized by long-range interactions. Okay, I'm done. Let me conclude with a short teaser. Last week there was a conference on multifractality here. I think that maybe still some people around. So let me just say that we have a recent observation of multifractality and anomalous diffusion in systems that have to do with long-range interactions. There are quantumizing models with positional disorder. And the inspiration that pushed us towards this study came from Rydberg atoms that essentially can realize quantumizing models with Van der Waals actions, decaying like 1 over r to the power 6. And you can, these days, position the atoms one by one, either in a regular way, or maybe you just don't do anything, and then your atoms are just trapped in a random arrangement. In fact, some experiments can interpolate between these two regimes. So you can look at the positional disorder as being a tuning of the experiment. Now, if you start from a perfectly regular array, in this case a square array, and you introduce small displacements, the ground state of this Hamiltonian remains a nice ferromagnet if it was a ferromagnet in the absence of disorder. But the excitation spectrum changes dramatically. And this is the excitation spectrum localization properties as a function of the energy of the excitations. We observe, in fact, the existence of localized modes, even in a regime in which the ground state remains ferromagnetic. And if you look into the extended part of the spectrum, well, it has some peculiarities. It seems to have a non-trivial multifractal spectrum, so you have seemingly extended non-ergodic states. And it's revealed by the if we look at the quench dynamics for disorder strengths for which you have both and then localized states, or even for, in theme of weak disorder, where you have extended but non-ergodic states, you observe anomalous diffusion, continuously varying dynamics as you change disorder. So I would be glad to discuss about this with the experts in the audience after my talk or during the question time. So let me conclude by stating that hopefully I made the case that long-range interactions introduce an extremely rich dynamics of information scrambling in quantum as they introduce a lot of diversity between the dynamics of correlation spreading, of entanglement relaxation, and of linear response dynamics. And spin wave theory, in fact, fully captures all this richness. So I think theory, at least with the limitations that I discussed before during the intermediate question time. And as an outlook, I think it would be very important now to exhibit microscopic calculation, not a calculation of the operator norms, but a calculation, a quench calculation, local quench calculation, in fact, that can exhibit the discrepancy between correlation dynamics and response dynamics, suggesting, in fact, experiments that flesh out this difference. As already commented before, also gearing up to do is to include nonlinear spin-wave approximation to test the robustness of its predictions. And with this, thank you very much for your attention.
So please use the microphone for the questions.
You pointed out that for long-range interactions, the operator spreading can behave differently than the correlation